there was a couple of things just came up there from conversation with a few people. The first thing from the panel discussion yesterday afternoon, I thought about something, and I thought it was worth mentioning today. So I worked at Lawrence Livermore Labs, but my family, so this is a Henry story again, my family, my mother's family came from a bakery, and I worked in that bakery since I was about 12 years old during the summer and so on. And I particularly liked being on the van, delivering the bread, dealing with customers, and doing the business end, okay? So I liked business, actually. And at one stage, I considered taking a course in business at university. I didn't. I went and I did my PhD. So I worked at Lawrence Livermore Labs doing my postdoc, but I was very keen there to work on some projects that Charlie and Bill had with industry partners like Cummins Engine Company and so on. And I really enjoyed that. So one thing that it didn't come up at the panel discussion yesterday, but it's something that I just wanted to mention today, is that just because you work in academia doesn't necessarily mean that you're just an academic doing blue skies research and you're removed from industrial applications. So now I very much enjoy working. We have projects currently with Siemens, Shell, and Ford Motor Company, okay? And there they have some applications. And I do, okay, the research that we do is very basic, fundamental, and at a low TRL level, okay? However, talking with the technical contact at the company gives me some perspective on how it's used ultimately to advance their product and help the company. And I very much like that. And it gives me a sense of achievement and meaning for the research that we do. And I didn't, on reflection yesterday afternoon, I was thinking, it would be nice to say that to you, that just because, or just if you go into academia, doesn't necessarily mean that you have to be removed from doing something that's applied and that is worthwhile, okay? So I just wanted to say that. Second thing, and more technical, people were asking me here, how did I get these numbers? So if we go back to the flux analysis for neopentane, where do these numbers come from? Okay, and another thing was, what's this number here? That was just the reaction number in the mechanism. So that's, don't worry about that, okay? But where did I get these numbers? So what I do, to do flux analysis, is very important to do that when you're modeling. So what I do is I look at, I look for a time when the fuel is maybe between 10 and 20% consumed. And I then I track what's happening to the fuel at 10 or 20% fuel consumed. So where does the fuel go, and follow the chemistry down. And you can work out the net rate of production of the fuel, and then translate it into a percentage consumption, ultimately. Okay? So that's how this flux analysis was performed. Yes. Okay? So it's just at this condition. So I took a time step, an output from a time step in the code. It was actually performed using HCT, but it's the same chem, right? And just did a rate of production analysis on the consumption of the fuel. So you can tell, okay, what's happening in the fuel, then you follow the radical, then you follow the alkyl peroxy radical, and so on. You can normalize everything so that you can make it, 100% going from the fuel down to the radical, and then all the way down through. Okay, so that's how this was performed. Okay, so again, that's something I think that's very important for you to really understand the chemistry to be able to do those rate of production analysis. Okay, so do those, because then you really do understand the chemistry, what's controlling everything. All right? Okay, so now we're at low temperature chemistry. Okay, so where do we get the rate constants for all these types of reactions? Okay, so, and I suppose I should have said this maybe yesterday, and possibly I did, but it's all very complicated, right? It's not simple in terms of the different regimes and so on. There's complicated chemistry all, even in this generic diagram, it's complicated. Okay, so what we do to try and remove those complications is to divide the chemistry into reaction classes, okay? And so at high temperatures, for instance, we have, we'd say, 9 important reaction classes that we consider. And if we break it down this way, then we can approach the problem in a systematic way, okay? And this is what's done then in these automatic generation codes that Bill Green has, RMG, for instance, and other ones. Frederique Badan-Leclerc's Thurga, or what is it she has? It's not X-gas. I can't think of it. Okay. So anyway, at high temperatures, we have unimolecular fuel decomposition. I've spoken about this before, CC, CH, or if there's an oxygen atom, CO or OO, bond cleavage. Okay? Then you have H atom abstraction from the fuel, forming an alkyl radical. The alkyl radical so formed then can decompose into a smaller alkyl radical and an olefin. Okay? The alkyl radical can react with O2 to give an olefin plus HO2, or it can isomerize to another alkyl radical. Okay? Then the olefins that are formed from alkyl radical decompositions can have to be consumed, so they undergo unimolecular decomposition or H atom abstraction, and addition of radical species to olefins. So I'll be talking about that a little later. So you can get addition of OH in particular and HO2 to olefins, right? And then alkynyl radical decomposition. So once you abstract a hydrogen atom from an alkene, you get alkynyl radicals, and they decompose, and then olefin decomposition. Okay? So you have all these high temperature reaction classes. And then at low temperatures, we have more reaction classes. I don't know, 15 or 16 more reaction classes. Okay? So we have alkyl radical addition to molecular oxygen. So now we form our RO2 species. Okay? And that RO2 can react with an alkyl radical to give an RO and an R primo radical. Or alkyl peroxy, the alkyl peroxy RO2 can isomerize to hydroperoxy alkyl radicals. Or RO2s can react with HO2, H2O2, CH3O2, other species producing different products. Okay. And then the alkyl hydroperoxide formed here can decompose to give an alkyl peroxy plus hydroxy radical. And then the alkyl peroxy can decompose. So after this isomerization, we have RO2 formed here. This isomerization forms a QOH. That QOH can give a cyclic ether. We can have RO2 giving olefin plus HO2. So this is an old slide now. Or the QOH can give other beta scission products. Olefin and aldehyde are carbonyl plus OH radical. Okay? And then we can have the second addition of the QOH to molecular oxygen. So we can get the O2 QOH. That can isomerize to give a carbonyl hydroperoxide plus OH. And then the carbonyl hydroperoxide decomposes to give a carbonyl alkoxy radical plus OH. Right? And then the cyclic ethers that are formed here have to be consumed. So we react them with OH and HO2 radicals. Okay? Because they're the most important at low temperatures. All right? So they're all the classes. And we consider reactions of those. Okay. So how do we treat them? Okay. And so I spoke about this paper already. This is the paper from Stephanie Villano working with Tony Dean, where they looked at alkyl radical plus O2 reactions. So they looked at the dissociation, concerted elimination, and isomerization channels of alkyl peroxy radicals. Okay? And it's well worth reading this paper. Okay? So they looked at this channel. So here, just to show you and keep this in mind, I keep referring to this. We have an alkyl radical plus O2. You get this RO2 radical. This is chemically activated, and it can stabilized to RO2. And we have this well depth, okay? And the depth of this well determines how stable or not, whether the equilibrium lies to the left or to the right, okay? And then that can isomerize to give hydroperoxy alkyl radical, or go through this concerted elimination, giving an olefin plus HO2, okay? So this is what this diagram is depicting here. Okay, so now I just want to focus on something here. This is a 5-membered ring isomerization, okay? And this doesn't happen directly like this anymore, okay? Or it's not understood to happen like this anymore, okay? So what we have is, here I have we have n-Pentane, we get the 2-pentyl radical, that adds to molecular oxygen, you get 2-pentyl peroxy radical, and this is the RO2. That can go through this 5-member transition state ring, forming the species, but actually it doesn't give this hydroperoxy alkyl radical, it gives olefin plus HO2 directly from this transition state, okay, in a concerted elimination, okay? Okay, but here's a 6-membered isomerization, okay? So here we have the same 2-pentyl peroxy radical that can abstract a hydrogen atom on this carbon atom through a 6-member transition state ring. So this is just showing you, really I just want to highlight, this is a 5-membered ring, transition state ring, this is a 6-member transition state ring, okay? And I just want you to focus on that for a second, okay? So if we look at it, here we have a frequency factor of 2 times 10 to the 11 for the A factor, and we have an activation energy of 26.5 kilocalories per mole, okay? They're not right, but anyway, just relatively, they're okay, okay? For a 6-member transition state ring, our frequency factor, so what's the difference? Look, in this molecule here, we're abstracting one of these hydrogen atoms. In this molecule, we're abstracting a similar hydrogen atom, okay? This is a carbon, which is bonded to 2 other carbons and 2 hydrogens. This is a carbon bonded to 2 other carbons and 2 hydrogens. So the local environment of a hydrogen atom on this carbon is similar to the local environment of a hydrogen atom on this carbon. So this should be equally, easily, or hard to abstract, okay? They should be about the same, but they're not, right? Why? Okay, so 2 reasons. First of all, in the transition state here, we have a 5-membered ring in this case, okay? In this case, we have a 6-membered ring, okay? So in this case, we have 1, 2, is it 1? Yeah, hang on, 1, 2, yeah. So we have 1, 2 rotors that are tied up in the transition state, okay? So they're no longer rotors, they're tied up. So we have a rotor here, 1, 2, 3. But we tie up this rotor and we tie up this rotor when we make the transition state, okay? But in this case, for the 6-membered ring, we tie up 1, 2, 3 rotors, okay? We tie up 1, 2, 3. They're no longer able to rotate. Because we tie up an extra rotor in the transition state, the frequency factor to form the 6-membered ring is about an order of magnitude, factor 8 to 10, lower than it is for the 5-membered ring, okay? So as you go higher in ring size, typically the frequency factor for the reaction decreases by almost an order of magnitude, between a factor of 8 and 10, right? So that's the first thing to bear in mind, right? Second thing here, though, is the activation energy. So that accounts for this decrease in frequency factor. But the activation energy actually decreases by 6 kilocalories per mole, going from a 5-membered ring to a 6-membered ring. If you look here at the ring, you can see it's a little bit puckered and not nice and symmetrical, okay? Whereas here, you see the 6-membered ring doesn't have ring strain. So here, in a 5-membered ring, there's a ring strain energy involved. For a 6-membered ring, we don't have the same ring strain, okay? And that accounts for that 6 kilocalorie per mole difference in activation energy. Okay? So it's easier to form a 6-membered ring than it is a 5-membered ring by about 6 kilocalories per mole. And that accounts for that difference in activation energy. Okay? So this is the transition state that will lead to the concerted elimination products. So it doesn't form this, it will form the olefin plus HO2. Okay? But don't worry about that. Okay. And so what Stephanie Villano did, she calculated then Ray constants for 23 different species. Okay? Both N-alkanes and branched, okay? For involving transition states of 5-membered transition states for primary, secondary, and tertiaries. Okay? And you can see, look, all the primaries are very similar, all the secondaries are very similar, and all the tertiaries. So you can come up with a rate rule then for the ring size. Okay? So if you have a primary hydrogen atom involved in the isomerization, the rate constant is lower. If it's secondary, it's a bit faster, and if it's tertiary, it's faster again. Okay? But they all fall on very similar curves. And the same for 6-membered ring. Okay? The secondary is a little bit more spread, but you have pretty good correlation for primary and tertiary. Okay? And then you could take this purple intermediate one as the secondary one. Okay? So you can see then you can come up with rate rules for the class of reaction. And this is from this publication. Okay. So these are the rate rules that I had published in the isooctane paper in 2002. These are the rate rules from the ab initio calculations from Stephanie Villano in 2011. Okay? But it's just showing you, look, if you go, forget about the frequency, the A and the N, okay? Because it's a little more complicated. I didn't have any N in here. But if we just look at the activation energies, okay? For a 5-member primary, it's 32 kilocalories per mole. For a 6-membered ring, it's 21.5, okay? For a 7-membered ring, it's about the same, actually, as a 6-membered ring, okay? So the ring strain for 7, there isn't much difference between 6 and 7. Okay? That's what it's saying. But there is a big drop going from 5 to 6. Okay? And then these frequency factors will also manifest themselves in lower frequency factor for 6-membered ring relative to a 5. It's harder to see it because you've got an A and a T to the N. Okay. So what did we do? So in Galway, John Bugler looked again at the pentane isomers, n-Pentane, isopentane, and neopentane. And he took these rate rules and so on, and we reapplied what we understood about low temperature chemistry to the pentane isomers. And we said, we asked ourselves, do we really understand low temperature chemistry or not? Can we explain the oxidation of n-Pentane, neopentane, and isopentane? And we could, because the lines that you saw earlier were the model predictions. Okay? Okay, so here it is. So, and I showed you this slide already, so we can. Okay? So he applied that. Actually, the rate rules taken from the Stephanie Villano, sorry, where am I? Yeah, taken from this and other Professor Miyoshi's group and so on, were then applied, okay, in this paper from Liming Kai and Heinz Pitch's group. Okay, so what Liming did was he took the rate rules that we were working on, and he said, okay, we can adjust the rate constants within the uncertainty of what we had said and others had published, okay? And we take a training set from NC7 to NC11. And it was just for ignition delay time, okay? And we'll optimize the rate rules for that, okay? And then we'll develop a mechanism based on that optimization for N-dodecane, NC12. And when they did that, they found that the model matched experimental data very well, okay? Which showed the success of the rate rules that were developed, okay, for the low temperature chemistry. So typically, in my opinion, the rate rules for N-alkanes, we still need some refinement and so on, but we do understand now a lot about rate rules, certainly for N-alkanes at low temperature, okay? And we applied these rate rules. These rate rules, I believe, can also be expanded to other species, like alcohols, for instance. Why not? Because if we think of an alcohol, you know, if we have an alkyl radical here, any type, so let's say you've got a C10 molecule. The carbons out here don't see the functional group, the alcohol functional group. And so you can apply the rate rules to all of the chemistry related to that alkane, just like you would a regular alkane. Okay? But there is a difference. So you do have this functional group, the OH. And I've presented it here for ethanol. Okay? And typically, alcohols are less reactive than their corresponding alkane. So for instance, N-pentanol has a research octane number of 80. Okay? But N-pentane has a research octane number of 61.7, 62. Okay? So typically, the octane number of an alcohol is much higher than that of its corresponding alkane. Okay? So what happens? Okay? If we have an OH bonded to this carbon, what does the O atom do? Okay, so we have an OH here, okay, bonded to this carbon. What does this oxygen atom do? Yeah. It draws electron density away from the carbon, okay? And what does that do to this CH bond then? It makes it weaker. Yeah. So if this was a secondary hydrogen atom, it would be 98.5. But because the oxygen atom draws electron density away from it, it might reduce it down to about 90 kilocalories per, or 92 kilocalories per mole. Okay? It's lower, so it's more easily abstracted. Okay? The hydrogen atom here is weaker. So the hydrogen atoms on the carbon atom, alpha to the OH alcohol function group, are the weakest. Okay? And these are the most easily abstractable. So you're always going to get primarily alpha, radicals alpha to the functional group, regardless of what's here. Okay? And Gabriel De Silva, working with Joe Bazzelli and John Farrell, showed that there's a concerted elimination reaction of this with an activation energy barrier of 11.4 kilocalories per mole. And I depicted it here. So we add this radical to molecular oxygen, we get the alkyl peroxy radical, and then we get this chemically activated, or this transition state, okay? And then that eliminates, so I should have the similar graph for the previous 5-membered isomerization. It eliminates acetaldehyde and HO2 directly. Okay, so the hydrogen atom moves here, so we have a 1, 2, 3, 4, 5-member transition state ring. Once we form that, we get CH3CHO and HO2 eliminated directly. Okay, with an activation energy of only 11.4 kilocalories per mole. It's very low. Okay, so anytime this happens to be in ethanol, okay, but this is just a methyl. But you can have any R here, and you're going to have a very similar rate constant for this reaction, just because this is a methyl. You could have this ethyl, propyl, butyl, anything you want, okay? It still involves the same transition state, and it's still going to eliminate R aldehyde, okay, plus HO2.
Is that true for the N alcohols?
It'll be true for branched alcohols, depending on the local environment. But you can set up a transition state that will look like this, and you can predict the product. Okay? Okay, so I was talking about you can then, because you have these rate rules, you can then have software to automatically generate low temperature reaction schemes. Okay? You know the reaction classes, and you can have rate rules for the rate constants for the reactions. Okay? So actually, and this all started back in about 1995. Okay? So the MAMOX code was one of the first that was generated by Eliseo Ranzi and Tiziano Faravelli at the Politecnico di Milano. Okay? And so also then computer-aided automatic generation for large aliphatic hydrocarbon molecules. Chevalier et al. Published a paper at the symposium on that. I think Charlie Westbrook was a co-author on that, and that was primarily led by Jürgen Warnatz from Germany. Okay, but it didn't include the reaction rate details in the paper. Okay, reaction was developed by Morley and Blue Rock in 93 to 95. Okay, and this was enhanced by Gladys Mauriac. She now works at Renault in France to generate mechanisms for n-Heptane and n-Decane. Okay, X-gas was what I was trying to think of a little earlier. Okay, so now X-gas, pardon me, is available from Frédéric Bertrand-Leclerc's group since 2005. And you can write to Frédéric Bertrand-Leclerc and ask her for a copy of this, and you can use it to automatically generate reaction mechanisms. Okay, so this uses a comprehensive C0 to C2 database with lumped secondary mechanism from KINGAS for the larger species. Okay, and it uses thermodynamics from THERGAS. Okay, there's a Genesis code from Van Geem's group at Ghent University, published in 2012 to 2015, and in the US, Bill Green at MIT, working with Richard West at Northwestern now. He was a postdoc with Bill a number of years ago, has reaction mechanism generator, RMG. A lot of you probably have heard of that, RMG. Okay. So the mechanism includes elementary reaction steps for some of the core chemistry, and then has rate rules to generate the detailed chemistry for a molecule. Okay. Okay, so we have this again. Okay, what do I want to say here? Oh, yeah. Okay, so if you read some of the older literature, okay, they'll say that, okay, and I'm a little bit animated about this, so so bear with me. Okay, so you know, I've described this already. We have the low temperature chemistry, we have the high temperature chemistry, and then we have this NTC region in between. Okay, and I've said that this NTC region stems from hydroperoxy alkyl radical if it adds to molecular oxygen or it undergoes propagation, or the RO2 giving you olefin plus HO2. Okay, so it's a little bit more complicated than just QOH. Okay, but the fulcrum of the system lies here. Okay, whether it goes to propagation or branching. Okay, so if hydroperoxy alkyl radicals add to molecular oxygen, we get branching. If they undergo propagation or the RO2 propagates, we get propagation and not branching. So we get NTC behavior. Okay, so why am I saying that? So in the older literature, people would say, well, NTC behavior stems from this R plus O2 giving you RO2 equilibrium, and that goes backwards. Okay? And I showed you the flux analysis earlier, okay, for neopentane. That flux analysis was performed at the top of the NTC region, okay? Right at the end of the NTC region, okay? And there you saw 90% of the alkyl radical still added to molecular oxygen. Okay? So it didn't stem, that negative temperature coefficient regime did not stem from that equilibrium shifting to R plus O2. Okay? It stemmed from QOH going to propagation or going on to add to molecular oxygen. But this QOH, it's a radical. And there is an addition to molecular oxygen. So there is an R plus O2. Okay? But it's this radical, not this one. Okay? So just bear that in mind. Okay, as I'm talking. Okay? So, but the older literature referred to this R. Okay? Or you could interpret it that that's what they were talking about. But it's actually this R that you should consider. Okay? So just be careful. Okay. But if we look at this, we have this concept of sealing temperature. So we have R plus O2 gives RO2. And the rate constant for addition has, it's 10 to the 9 liters per mole per second, or if some of you are used to it, it's 10 to the 12 centimeters cubed per mole per second. Okay? This is decimeter cubed. So it's 10 to the 12 centimeters cubed per mole per second. And in the reverse direction, so there's no activation energy in the forward direction. In the reverse direction, we have a frequency factor and an activation energy of 28 kilocalories per mole. Actually, sometimes higher, up to 36. Remember I was saying the well depth, about 36. Okay? So this is the reverse reaction. Okay? So there's competitive pathways. At high temperatures, alkyl radicals are favored over peroxy radicals, or pyrolysis is favored over oxidation. So there's this concept of sealing temperature, which is the transition temperature from one mechanism to the other. So either the alkyl radical adds to molecular oxygen or undergoes split addition. Okay? And we consider that the sealing temperature. Okay? So at the equilibrium, the addition, the forward, and the decomposition, the reverse reaction rates are equal. So we have rate constant for addition and rate constant for decomposition. And at equilibrium, they're going to be equal. So at equilibrium, the rate constant for addition times the concentration of alkyl radical times the concentration of O2 is equal to the rate constant for dissociation times the concentration of RO2. Okay? Okay? And if we then rearrange all this, we can then calculate a pressure which is equivalent to all of this value here. Okay? And we can look at it as a dependence on the mole fraction of O2. Okay? So it's, and temperature. Okay? So if we keep O2 constant, okay, we can then plot pressure versus temperature. Okay? And this is what we see. We've got this red curve here. Okay? So here, the pressures in atmospheres, R is 0.082 liters per liter atmospheres per degree Kelvin per mole. Okay? But you get this graph here. Okay? And so in this graph, the equilibrium shifts in this region to the left. Okay? So it now favors R plus O2, not RO2, and so the system leads to alkyl radical decomposition. Okay. In this region here, above this red line, the equilibrium lies to the right. Okay, we have R plus O2 giving us RO2. Okay, so if we look at it, if we just take, for instance, 950 Kelvin, what does that mean? It means that if we're at low pressure and at 950 Kelvin, up to about 2 atmospheres at 950 Kelvin, the equilibrium lies to the left. We have R plus O2, not RO2. Okay? The equilibrium lies to the left. However, above 2 atmospheres, the equilibrium lies to the right. Okay? And we're going to have more RO2 than R plus O2. And the system's going to go on to chain branching. Okay? So if we go to 1200 Kelvin, you see now that at 1200 Kelvin, okay, up to about 20 atmospheres, the system lies to the left, R plus O2, okay? But above that pressure, the system lies to the right. We've got R plus O2 giving us RO2. Okay. So what happens is, if we go higher in pressure, the equilibrium shifts to higher temperature. Okay? And you see here the peak in reactivity at low temperature here occurs at about 850 Kelvin, but here, or sorry, 750 Kelvin, I should say, but here it's about 850 Kelvin. So everything is shifted by about 100 Kelvin at higher pressure. Okay? So it's shifting at higher pressure, the chemistry shifts to higher temperature. Okay? Or the low temperature chemistry shifts to high temperature. These are data for n-Heptane oxidation, which were published in 1993. Okay? Okay, and so this is just showing you again this R plus O2, giving you RO2, and the well depth here, whether it shifts to the left or if it shifts to the left or the right. Okay, so if we lower this well depth, it shifts the equilibrium back to the left. We get R plus O2 rather than RO2. It's not as easy. Stabilize RO2. Okay. And so if we look at the bond association energies of alkanes, okay, relative to olefins, okay, what we see here is, look, for secondary hydrogen atom, it's about 96 kilocalories per mole. Primary, 100.5, okay? But here, and here, we primarily have similar bond association energies out here. They're calculated to be about the same. These are, the blue values come from G4. These are ab initio calculations, and the black ones are from CBS-QB3 calculations, okay? So, but you can see here, look, the CBS-QB3, if you compare, here the hydrogen atom is 100.46, here it's 100.5. They're the same, okay? However, if we look here at the allylic hydrogen atom, so a hydrogen atom beta to the CC double bond, the bond strength is 83 kilocalories per mole, much lower than any other primary or secondary hydrogen atom in the molecule. Okay, but so if we abstract that hydrogen atom, okay, and we add molecular oxygen, okay, and we work out what the well depth is for that R plus O2 well depth, it comes out to be about either 19.4 or 19.7, depending on the method, okay, which means that the R plus O2 equilibrium shifts to the left. We don't get, it doesn't stabilize very much to RO2, it stays as R plus O2, okay? In comparison, for instance, to this normal secondary in an alkane, where the well depth is 36 kilocalories per mole. Okay? It's much shallower. So what does that mean for the chemistry of olefins in comparison to alkanes at low temperature? R plus O2. So what will that, if that, and that's true, correct? So what will then happen? Yeah, so in an alkane, this is more likely, so this is more likely to form RO2. But for the alkene, it's not likely to form the RO2. It's going to want to stay as R plus O2, not RO2. So if you have an alkene, it's going to show relatively much less low temperature reactivity compared to an alkane. and that's what you see. Okay, so alkanes and alkenes have different low temperature chemistry, much different low temperature chemistry. Why? Because this is much more easily abstracted, but the well depth here is only 19.4, 19.7 kilocalories per mole, not 36 kilocalories per mole. Way shallower. Okay, so I showed you this slide already. We see the negative temperature coefficient behavior for n-Heptane. Okay, and we have all the different species. And we also have this complication due to H plus O2 chemistry that I've already shown you as well. Okay, so this is just showing you then reactivities. Okay, so it's taking into account what I said yesterday and what I'm saying today. Okay, or over the last couple of days. Okay, so these are just ignition delay times that we measured in my lab for different molecules here, sec-butanol, isobutanol, okay? But these are at high temperature and low pressure conditions. So here we're at about 1250 Kelvin up to 1600, 1700 Kelvin. And we have 1% fuel ranging from 1150 to 1750. So this is rich, this is stoichiometric, and this is lean. Phi is equal to 2, phi is equal to 1, phi is equal to 0.5. Okay? And you see here, lean mixtures are faster to ignite compared to rich mixtures. Why? You should all be able to answer this now. Okay? So if we're at the same temperature here, look, the lean mixture is much faster to ignite. It's decreasing by maybe a factor of 2 each time. Why is that? Okay. Not as a third body. So if we're at high temperature, and no, you're correct, primarily correct. So we have higher oxygen concentration, so what you said, which is perfect, right? But we're at high temperature, so what's the important chain branching reaction at high temperature? Okay, we've H plus O2 gives O plus OH. Okay? So from these fuels, will we get similar H atom? The answer is yes. Okay? So what's changing is O2. And you see the lean mixture there. Look, the O2 is written 3% O2. Stoichiometric mixture, 6% O2. Lean mixture, 12% O2. Okay? So we're doubling the concentration of O2 each time. What happens the ignition delay time at the same temperature? Pardon me? It approximately doubles. Okay? And it's all due to this one reaction, chain branching reaction. Okay? Well, it's a 3-step process, but this is the rate determining one. Okay? And so at high temperatures, lean mixtures are faster to ignite because they have more oxygen. Okay? And you increase the concentration of oxygen, the rate of that reaction increases proportionately. Okay? So, okay, but this then is lower temperatures. Okay? So this is isopentanol. So this was for butanol. I picked something that was similar, but it could be any fuel. Okay? So here's isopentanol. This is at 21 bar, and here we have phi is equal to 0.5, 1, and 2. And now I'm messing with your head, because now rich mixtures are faster to ignite than lean mixtures at the same temperature. Okay? Because we're in a different regime. Okay? So the chemistry controlling this is different. And here this is 1,000 Kelvin. We're going up to, this is 1250, 1,300, more. So here we're at low pressure, relatively speaking, 3.5 atmospheres. Okay? And we're still, so we're overlapping here in temperature here. But here still, rich mixtures are faster, lean mixtures are slower. It was the other way around earlier. Okay? Because we're still in low intermediate temperature regime kinetics here. Okay? Where the concentration of alkyl radical adds to molecular oxygen, that will give you olefin plus HO2, and HO2 chemistry is important in here. So the higher the concentration of the fuel, the higher the concentration of alkyl radical you're going to get, the higher the concentration of HO2 you're going to get, the higher the chain branching. Okay? So rich mixtures are faster to ignite here compared to lean mixtures. Okay? So you need to know where you are. Okay? And then this is just showing you a couple examples. I think I had one earlier for the n-Pentane, which is a very nice one. This is just showing you a couple more where we have these natural gas mixtures. And you can see here now, we're at low temperature. Rich mixtures are faster to ignite in comparison to lean mixtures. This is stoichiometric, this is lean. And then it's changing over here at 1300 Kelvin. Lean mixtures are becoming faster to ignite compared to rich mixtures. Okay? And this happens all the time for all fuels. Okay? So you transition in chemistry. Okay? And it's due to the chain branching mechanisms associated with fuel oxidation. Okay. Here it is again, N-propylbenzene at 30 atmospheres. Here are rich mixtures. Here's our leanest mixture. At lower temperatures, the rich mixtures are fastest to ignite. And here the turnover, again, 1300 Kelvin or so. Okay? Depending on the pressure, because of that sealing temperature issue. Okay? So it changes to higher temperature at higher pressures. Okay? But the switch over occurs, but you get here now lean mixtures are faster than the rich mixtures. Okay? And that, again, it's seen both in the experiment, and which are the points, and the model predictions, which are the lines. Okay? So we're capturing the chemistry. Okay, maybe this is a bit too advanced. Some of you may or may not follow it, but anyway, let me try and just go through it. This is just showing you predicted ignition delay times as a function of temperature for M-propane, or for propane. And propane is one of the first alkanes for which you have negative temperature coefficient behavior. You get this cool flame. Okay? So at low temperature, 600 Kelvin, you have very little reactivity. Reactivity starts. Then we get a first stage ignition, then a sort of a lapse in reactivity, and then a second stage ignition. But the first and the second stage ignition are very close to one another. Okay? If we go slightly higher in temperature, we'd say 625 or, I don't know, maybe close to 650, I don't know, 630 or so. Now we see much earlier reactivity. Okay? Then we see the step rise in reactivity. The step isn't as high this time as it was at lower temperature. Okay? And then we see a second stage ignition. Okay? We go higher in temperature again, about, I don't know, 660 Kelvin or so. And we see faster reactivity. We see a smaller step again than we did before. Then kind of a plateau again, and then a second stage reactivity. And actually, the total reactivity is a little bit, it's about the same as it was at 630, maybe a little bit longer. Arbitrary. Okay. No, this is constant volume. Okay? This is constant volume simulation. Okay? So we're just taking constant volume. Okay? And then if we go to, it's not quite right, to be honest with you. But anyway, it's good enough to illustrate what I want to illustrate. Okay? I should really have gotten the most modern mechanism. Okay? But if we go to just below 700, we'd say 680 Kelvin, you see this step is almost, you can hardly see it now, but there is one there. Okay? And then we have this, again, it's quite slow to react. It's like even slower than at lower temperature. So we're definitely in the NTC. And then above that temperature, okay, we see just one step, one stage reactivity. We don't see two-stage anymore. The step goes away. Okay, so what's going on there? Okay, so what's going on there is this, and I'll finish with this. So if you just give me your attention for the next few minutes, then we take a break. All right? So what happens? If we're at very low temperature, so we go back here, very low temperature, what happens? Okay, just follow the blue, the yellow-blue road, right? So we have fuel, we get alkyl radical, and we go chain branching, we get 1, 2, 3 reactive radicals, ultimately. Okay? But what happens actually, in actual fact, is we get to here, and we go all the way to here. So we get a stable species and OH. Okay? So in the case of propane, we arrive at this molecule. C, C, C. We have OOH, double bond O, plus OH. I'm ignoring the hydrogens on the molecule, okay? So we arrive here, okay? And this is true for all alkanes, okay? But now what do we have to do to get the branching? So this is now a propagation still, okay? So remember, we formed a fuel radical, and we've generated one radical and a stable molecule. We're still at propagation, not branching. So what is the branching step?
Won't you?
Yeah. So if we break this OO bond, we get OH and the radical. And now we've gotten our 3 radicals from one fuel radical. That's the branching. So critical to the branching is breaking that OO bond. Okay? But to break this OO bond, you have an activation energy of 43 kilocalories per mole. Okay? It requires 43 kilocalories per mole to break that bond. Okay? It's not as high as 101 or 88 or 90. Okay? It's 43. It's half that. But it's still appreciable at 600 Kelvin. So at 600 Kelvin, okay, we can't break it for a good while. Okay? So think of I always think of the reactivity like a viscous flow. Okay? What gives us heat release? Production of water or CO2. They give you heat release. Okay? Production of water or CO2. Okay? So in this system, what's going to give us heat release? OH plus fuel giving us water, or OH, pretty much OH plus fuel, right? That'll produce water. That's going to give us the heat release, which will then drive up the temperature, which will get us over the energy barrier, the 43 kilocalorie per mole energy barrier, to give us branching, which will give us more OHs, which will go back to give us more alkyl radicals, which will give us more branching. Okay? So it's all like, it's very slow to start with. Okay? That's why I think of it as a viscous flow. And then it gets stronger and stronger as you go higher in temperature. And it gives you more heat and feeds back. Okay? So if you're down here at 600 Kelvin, okay, it takes a lot of time for that process to happen, but it will happen eventually. So we build up a lot, so the system can go here quite readily. Okay? The activation energies here are lower. They're maybe 30 kilocalories per mole or lower. Right? So we can get to here readily. But then we have to wait to cleave this OO bond with the highest activation energy barrier of the whole process. So we build up lots of these carbonyl hydroperoxide species. And it's only after a certain period of time then, when they do start to decompose, but very slowly, that feeds back. There's a feedback mechanism like a viscous flow, and then it gets a little bit hotter. They start to break more readily, gets a little bit hotter, break more readily, and so on. And then you get a kind of a burst of them released. And you get this first stage ignition. Okay? Now the system gets over that threshold, 800, 900 Kelvin threshold, and you start to react even further, and you get all the intermediate and high temperature kinetics, and you get the second stage ignition. Okay? This is actually very complicated simulation, if you look at it, because you're starting off at 600 Kelvin, right, in your simulation. But when the fuel ignites, it's reached 12, 13, 14, 1500 Kelvin, 1200 typically, 12 or 1300 when it ignites. Okay? So, and all the chemistry evolves through the different stages, low, intermediate, and high temperature kinetics, as it evolves through it. So it doesn't stay at 600 Kelvin kinetics. Okay? So actually, a shock tube simulation is very, very complicated, even though it's one of the simplest ones to perform using ChemChin. You set the initial condition, say it's constant volume, go ahead and simulate. Okay? But the chemistry evolution is very complicated, actually. Right? So then if you look at 625 Kelvin, 630 Kelvin here for the blue one, you're at higher temperature, so you don't, because you're at higher temperature, you can flow through these carbonyl hydroperoxides a little more easily. Not as many of them build up, so the step that you get from their release isn't as high. Okay? And then you have a longer, because you have, you're not as delayed, you have a longer stage to the second ignition. Okay? Because you're not getting as much heat release in the first stage. Okay? And this is correspondingly true then at even higher temperature. Okay? And eventually that step goes away. You don't get the two-step ignition anymore because you don't build up any ketohydroperoxides anymore. The activation energy, 43 kilocalories per mole, can now be overcome directly. So you don't build them up, and you don't see two-stage ignition. This is actually a bad illustration. It's an old plot. This was from Tiziano Faravelli, but actually I should use a more modern one. Okay? Because the temperatures at which that step goes away is typically around 850 Kelvin. Okay? So you'll see in the literature, if you look at, first stage ignition and total ignition delay times plotted, you'll see that the first stage ignition typically goes away around 800, 850 Kelvin. Not here at 700, as depicted. Okay? It's normally around 800, 850. Okay? So remember, why does that step go away? Yeah, we can easily break this OO bond now because you're at a high enough temperature to overcome that activation energy. And why 850? Because remember H2O2 decomposition. What's that? OO bond cleavage. It's the same. Okay? So once you get over 850 Kelvin, HO2 chemistry is important for the same reason. okay? Because that H2O2 no longer is building up. It decomposes to two OH radicals, and that starts to control everything. Okay? So it's exactly the same reason. And it's similar activation energy again. Okay? Except you've got HOO, and instead of this being some sort of a carbon, it's another H. But it's the same thing. Okay? So let's take a break. We come back at 4:15.